자, 오늘은 지난번에 했던 데서부터 다시 시작할게요. 그러니까 지난번에 그 effective action 구했자 SYK 모델에서 오늘은 이제 파인먼 다이어그램에서 시작해가지고 똑같은 슈링어 다이슨 이퀘이션 구하는 것부터 해볼게요. 그 다음에 이제 예고를 좀 해보자면은 4포인트 펑션, 왜냐면 SYK 모델에서는 4포인트 펑션 계산해가지고 OTOC 구해서 그 라이프너프 엑스포넌트라는 걸 계산하는 게 중요한 포인트거든요. 그래서 그것도 할 거고, 그 다음에 JT 그래비티와의 연관성도 그 네 번째 시간에 커버할 계획입니다. 그래서 okay. Okay. So okay, last time, so okay. So last time we obtained these Schwinger-Dyson equations. We obtained Schwinger-Dyson equations. Okay. And Schwinger-Dyson equations, for those who don't know, are self-consistency relations that arise because of recursion relations in the Feynman diagram. So Schwinger-Dyson equations solve for the Green's function in the theory. Okay, for the Green's function. In the theory. And we obtained this by varying an effective action. Okay, but the result was that sigma, which can be interpreted as the self-energy, is given by coupling squared times the Green's function. And this is, for general Q, this is going to be Q minus 1. Okay, and then we have this just defines sigma as the self-energy, if you like, this equation, and then this equation actually solves for sigma. Okay, and then we made an ansatz that's diagonal in the replicas. So remember that the alpha and beta here are replica indices, right? So, and we said we want to make an ansatz that's diagonal in the replicas. So G alpha beta is delta alpha beta times G. So G tau prime and sigma alpha beta delta sigma tau prime. Okay, so let's derive these equations today from Feynman diagrams in the large N expansion. And it's an important point that we need to look at the factor of N that comes with each Feynman diagram, and we only want to look at the leading order diagrams. So diagrams that scale as N to the 0th power. Okay, so let's derive these equations from, let's look at Feynman diagrams and Feynman diagrams for the 2-point function in a large N expansion. So the Feynman rules, how do we draw the Feynman rules in this theory? Okay, they come from the microscopic Hamiltonian. Okay, so the Feynman rules in the theory are as follows. If we think back to the Hamiltonian that I wrote down in the first lecture, okay, we have a single line for the bare propagator. So this is just the free fermion propagator. This is the free Baire propagator for the fermion. So what is the free propagator? It's just the kinetic term of the Majorana fermion to the inverse. Okay, so the free Green's function is just the kinetic term dt inverse without the self energy. Okay, and in position space, it's actually just a sign function in time. So G is, if you Fourier transform this, you get a sign function in the time difference, the arguments for the two fermions, okay? And then the sort of the interesting feature of in this theory, because of the disorder average, is that we have vertices that look like this. So from each vertex here, we have a q number of lines coming out, a q number of fermions, each interacting at each vertex. But then the disorder average, remember there was a disorder average over J, and J squared was given by a fixed value. That J squared average can be thought of as a propagator for this dotted field, for this, right? Basically, we treat the couplings as another field. And then because we took a Gaussian integral, right? That's sort of like this J behaving as an effective field, and the value of this propagator is going to be given by the average of this J squared that we wrote down last time. Okay. So any questions here? What's the value? So what's the value of this propagator? It's given by J, regardless of the side indices here. So the important point is that this vertex and this vertex, in order to be joined by a disorder average, needs to have the same side indices, right? So this needs to be JKL. And as long as two vertices have the same side indices around them, then they can be joined by the disorder average propagator. Okay, so this is J squared times Q minus 1 factorial over n to the Q minus 1. Okay, and so this is a disorder average. Disorder average over two interactions, for two. Okay, so what are some diagrams that contribute at leading order in N? Okay, so maybe I'll some diagrams that contribute at leading order. So the full propagator is going to be given by the Baire propagator plus what's one diagram that contributes? It looks like this, right? This is a simple diagram that contributes. Okay. Now let's count the factors of n of this diagram. How do we count the factors of n here? Each Baire propagator, it's there. insertions of vertices. 네, 꼭지점. 자, each propagator has no factor of n, each free propagator, right? And we have this insertion here. So this diagram goes like 1 over n to the q minus 1. But there is a summation. We have to sum over the site index in each internal propagator, right? Does everybody understand this? So there's n to the q minus 1. So for general q, there's going to be q minus 1 site indices that we sum over. So this is going to be order n to the 0, this diagram. And so is the next diagram that has another insertion of this interaction in one of the vertices like this. This diagram is also going to scale like, well, let's see. Let's count the powers of n of this diagram. So we have n, we have 2 insertions of this disorder average. So we have n to the squared. But then you can see that we also have a compensating factor of n to the q minus 1 in each ball. So this is also at order n to the 0. What's a diagram that won't scale like n to the 0? What about this diagram? We have something like this. Let's see. And then we try to connect I try to insert an interaction vertex in this way, and if I count the factors of n, let's count the factors of n. So I have n, 1 over n to the q minus 1 squared. But how many internal propagators are we summing over? We have n to the q minus 1, because there are three free propagators here. Let's see. I, j, k, l. And this could be, let's see, I, j, k, l, and then this could be m. J, m. This could be I, j, k, l, m, n, p. But then these 2 vertices are connected by this dotted line, so they need to have the same set of indices. So that means that j and sorry, I'm gonna do I, j, k, l, and then this also needs to be I and j here, right? Because this indices I, j, k, l need to match up with the indices here, I, j, k, l. And then I, j, k, l, I, j, and then let's write m and n here. Because these 2 are connected by a dotted line, the indices need to be the same. And so we need an m here. Okay, and we have an n, and we have a j. I think this is the only way that we could match up. So we have a total of 1, 2, 3, 4, 5, 6 summations. That's that gives us, I think, us a factor of 1 over n squared. Sorry, 4 summations, 4 internal summations. So that's why it gives us a factor of 1 over n squared, right? In order for the diagram to be order n to the 0, we would have needed 6 internal summations. Okay. So this is a diagram that's not allowed, where you have a ball like this. Okay, so basically all the diagrams that are of order n to the 0 are going to have a so-called rainbow structure. Okay, so the leading diagrams in this theory have this rainbow structure where you have the disorder average inserted like a ball recursively. Okay. Now it becomes clear that we have this kind of relation. Hopefully that's kind of clear from the diagrams that recursively the self-energy, the 1pi diagrams, is going to be given by j squared times sigma to the q minus 1. Okay. Okay. So the sum of diagrams, so I call them rainbow diagrams, but they're also called melonic diagrams because they kind of look like melons here with stripes. Okay, so the sum of diagrams satisfy the following self-consistency condition. Satisfy the following self-consistency equations. Okay. So start from here. So let's first define a self-energy, which as I mentioned last time, includes 1pi diagrams. So we first define a self-energy. Okay, which includes all one particle irreducible or 1pi, one particle irreducible contributions to the propagator. Okay, so I'm going to denote the self-energy by this black circle. So this self-energy is going to include this diagram. Okay, obviously. So the meaning of 1pi is that you cut one propagator. You can't divide the diagram into 2 by cutting a single propagator. Okay, that's the meaning of one particle irreducible. So this diagram is clearly one particle irreducible. You can't divide it into 2 by cutting a single line. And so is the diagram that I drew before, which has another melon inside. Okay, this is also one particle irreducible, and so on. And then the full propagator, which I'm gonna, well, let's write it like this. The full propagator is going to be given by plus these black blobs joined in series. All of those are going to be order n to the 0. Okay, so okay, so by translational symmetry, we can write the sigma. The self-energy is just going to be a function of the difference between the 2 times. So why do we have translational symmetry in our setup? because we were in a thermal state. Okay? Or translational symmetry. Okay, sigma is only a function of the difference. Okay? So that means we can Fourier transform with respect to the time difference and go to frequency space. And in frequency space, we have the relation between the full Green's function and the self-energy, which is given by 1 over G is I omega minus sigma. Okay, this is just a general relation between the Green's function and the self-energy. It's also the second equation of motion that we derive from the effective action. And in addition to this, we have the recursion relation, which is we also have recursion relation that the blob. What's the recursion relation? The blob is going to be given by the full propagator, three powers of the full propagator. Okay, so this is the recursion relation that we have that's specific to the model. And if in equations, this is sigma is equal to J squared times G to the Q minus 1. Okay. So note that both G and sigma here are anti-symmetric functions of the of tau and tau prime. So G and sigma. So when we solve the Schwinger-Dyson equations, we have to keep in mind that they are anti-symmetric functions of anti-symmetric in tau and tau prime, which can assume values between 0 and beta. And also remember that they have anti-periodic boundary condition over the thermal circle. So G and similarly for sigma. Okay, with anti-periodic boundary conditions. So in general, these two equations can be solved numerically, right? But when we go to the limit that we discussed before of large n and low, well, we already took the large n limit because these equations are valid only to leading order in large n, but we also need to go to large inverse temperatures in order for them to be analytically solvable, okay? So they can be, equations can be solved numerically, okay, for general values of the temperature, but for both the inverse temperature and the time difference much greater than the coupling inverse, we have an analytic solution. So the simplest solution is the solution at 0 temperature, okay? So the 0 temperature solution is the Green's function has the following form. tau 1, tau 2 is given by minus b to the delta j tau 1. Okay, this is j times tau 1 minus tau 2, the time difference. And there's an overall power that's minus 2 times delta, where delta is going to be 1 over q. So if you like, delta is the conformal dimension of the Majorana fermion. So what happens is that if you go to low temperatures, there's an emergent conformal symmetry in this model. Okay, when we started out with the microscopic Hamiltonian, it wasn't obvious at all that there was going to be a conformal symmetry. But we've gone to low temperatures and we look at the 2-point function, and it looks like the 2-point function in a conformal theory. Okay, there's a sign here to give you the right boundary condition. Okay, so B here is a constant that depends on Q. So B is Q minus 2 times tangent pi over Q over 2 pi Q. And delta is 1 over Q. Okay, does everybody recognize that this looks like the 2-point function in a conformal theory? It goes like the distance to the minus 2 times some dimension. Okay. Now for finite values of beta, for finite but large beta j, you can do a reparameterization. You can apply some diffeomorphism to the time and get the solution, which goes, which instead of just the time difference is a sine function of the time difference divided by, divided by 2. So that's like going to from the real line to a circle. 네. 네네. 네. 어디서부터요? 네네네. 비어있는 원은 죄송합니다. 비어있는 원은 아까 이거 full Green's function이에요. 네.
그 다음에 마지막에 말씀하실 때 제로센터의 솔루션에서 리포트는 전혀 안 된다는 거를 리포트에 풀려 나왔거든요.
네. 근데 저 리밋으로 가야 돼요. 네. 자, 베이타가 무한대로 가면 어떻게 심플리파이가 됩니까, 여기서? 뭐가 어떻게 될까요, 여기서? 사실 이 키네틱 텀의 에펙트가 사라져요. 왜냐면 키네틱 텀이 키네틱 텀은 UV perturbation으로 봐야 돼요, 이 theory에서. 라그란지안을 생각했을 때 키네틱 텀은 UV perturbation으로 봐야 되거든요. 왜냐면 그 텀이 없으면은 시메트리가 있어요. conformal symmetry가 있는데 그 텀을 넣으면 이제 우리가 CFT language에서 생각해 보면 UV에서 perturbation을 튼 거거든요. 그래서 일단 이 zero temperature solution은 이거를 무시할 수 있다는 approximation에서 풀면은 저렇게 나옵니다. Okay, so the question was, so we have these equations and we get that solution in the zero temperature limit, and what happens in the zero temperature limit is that we can ignore this term I omega, because the kinetic term in the Lagrangian you should think of as a UV perturbation. Without the kinetic term, you have a conformal symmetry, but the kinetic term breaks the conformal symmetry. And so in the limit that you ignore this term, you get this solution. So now, if you know something about CFTs, you know that that a conformal transformation can take the half plane, right, to the disk in 2 dimensions using, right, This is a conformal mapping. So here we are working in 0+1 dimension. So we think of a conformal mapping that takes the line to the unit circle. And that conformal mapping will take this 2-point function at 0 temperature to the 2-point function at finite but large temperature. And it's going to be given by, instead of just the time difference to the -2 delta, it's going to be given by sine of time difference to the -2 delta. So let me write down the Green's function at large, finite but large values of beta. Okay, so I've suddenly started talking about conformal symmetries, but we'll also discuss that kind of explicitly, how what that symmetry is in terms of the Schwinger-Dyson equations. But for now, let's just note that for finite values of beta, there is an emergent conformal symmetry. Okay, well, for finite values of beta, the Green's function at intermediate time scales, which are time scales greater than J inverse, it has this form, okay? So I just conveniently taken out some overall factor here, and it has a so this is just a conformal, okay, for tau1 minus tau2 greater than J inverse, and the conformal 2-point function here, which is a function of, if you like, the angle, right? So I've normalized the time to be an angle here, 2 pi times tau over beta. So the conformal function as a function of two angles is, conformal 2-point function as a function of two angles is going to be given by minus b to the delta, phi 1, 2 to the -2 delta, sine of phi 1, 2, where here phi 1, 2 is 2 times sine of phi 1 minus phi 2 over 2. Okay? So basically, at finite temperatures, we have the sine function, sine of angle, difference in angle over 2, rather than just the time difference to the -2 delta. Okay? Okay. So let's step back a little bit and think about what was special about this model. Because we could think of just having a model with all random, well, just an arbitrary model with all-to-all interactions, right? So a feature of the Hamiltonian that we wrote down before was that any two fermions were going to interact, right, via some term in the Hamiltonian. So that's called all-to-all interactions, right? So remember, the picture is that we have a dot, a spatial dot, and on this dot there lives an large n number of Majorana fermions, and all-to-all means that each pair of fermions are all interacting. They're all interacting. So it's very non-local from the point of view of the fermions on the different sites. Is that right? So does everybody get that this is very non-local? So if you had a spatial dimension and you had a lattice, think about a fermion on each side of the lattice. In general, if you have a local Hamiltonian, right, the Majorana fermion is going to interact with some nearby neighbors. So there's a notion of locality here. But here in our model, we have a spatial dot. And between all the Majorana fermions, there's no notion of locality. The interactions are all-to-all and non-local. So In general, when we have all-to-all interactions, we are going to be able to write down these self-consistency or Schwinger-Dyson equations. Okay? But the physically, the special thing about the SYK model is that there is no ordering of the fermions as you go down to low temperatures. So something that happens a lot in something that could generically happen is that all the for example, if you have a spin model, all the spins would align at low temperatures, right? They would freeze into an ordered state. And the important thing about this state, which people in condensed matter have called the non-Fermi liquid, right? So it's a strongly coupled state of matter in which there is no ordering. And that is closely related to the fact that it has this gravitational description. So everybody have people heard about Fermi liquids? What's a Fermi liquid? So a Fermi liquid is, so Landau, right? Landau first came up with the idea of Fermi liquids to describe electrons that are interacting with each other. Even though the electrons are interacting with each other, the idea is that the excitations in the system can be described by quasi-particles. And these quasi-particles or excitations are emergent excitations, but they still behave like sort of free particles, and that's why they're called quasi-particles. They're weakly interacting. But there's no way, in the SYK model, we don't have quasi-particles, okay? We don't have a weakly interacting description of the system. And so that's called a non-Fermi liquid. And it turns out that non-Fermi liquids are strongly related to the system having a gravitational description. Okay, this is something that people studied even before the SYK model, just by comparing the two-point functions and things like the conductivity in your system. So the Green's function and the conductivity that you calculate in this many-body quantum system, you can reproduce if the many-body quantum system is a non-Fermi liquid, can be reproduced by calculations in a dual gravity theory. So all of this was known. Well, the fact that the Sachdev and Ye, okay, so they wrote down a similar model as the SYK model, and they noted that there's a conformal symmetry, as can be seen from the two-point function. The new ingredient in the SYK model is that you can actually calculate the four-point function and look at something called the out-of-time order correlator and see an exponentially growing, a piece of the four-point function that grows exponentially in time. Okay, so we'll get to that in a minute. Okay, so what happens to the SYK model when we go to very, very low temperatures? It turns out that the system actually does transition to a glassy phase. Okay, a glassy phase means that the excitations are frozen. Okay, but the transition happens at temperatures that are exponentially small in large N. Okay, so for example, for the Q equals 4 SYK model, a transition to a glassy phase is expected at temperatures that go like e to the minus square root of n. So for all perturbatively in large N, we can just ignore this for most purposes. Okay, so for Q equals 4 SYK model, okay, transition to glassy phase. It's expected. T. Okay. So the transition temperature is suppressed in large N, okay? And the mean field solution, right, the the solution that we've obtained is valid, is accurate, as long as the mean field solution we have obtained, solution given above, is accurate for temperatures. Okay, so if we translate this to beta, what do we have? We have beta J smaller than n. Okay, so we need to be in this regime in order for basically the quantum fluctuations to be small. Okay, and this is the regime where our solution to the Schwinger-Dyson equations are valid. Okay. So at lower temperatures, of course, quantum fluctuations around the saddle point should be taken in. They become strong and can't be ignored anymore. So basically, we don't have a large n expansion. At lower temperatures, quantum fluctuations should be taken into account. Become strong. This is kind of obvious, right? That in order for the 1 over n expansion to be valid, we need to be in the regime where n is greater than beta j. Okay. Okay, now we want to sort of have a compact description of the low energy degrees of freedom in the model. Okay. Is everybody comfortable with this idea that we can have an effective description of the emergent degrees of freedom? So the whole point is that this is a strongly coupled theory, right? So there's going to be some emergent degrees of freedom that need to be described using an effective description rather than, right? So that's where the non-trivial physics comes in. Okay. So what are the dominant degrees of freedom at low energies? Okay. Degree of freedom. Low energy degrees of freedom are dominant at low energy degrees of freedom in the model that are dominant at large beta J. Okay. They actually correspond to reparameterizations of the Green's function. Correspond to reparameterizations of Green's function. So how does this come about? Okay. So as I mentioned, when beta j is much, much greater than 1, okay, the derivative term, the kinetic term, or the derivative term d tau is small compared to the self energy. Okay, and without this term, there's actually the Schwinger-Dyson equations are actually invariant under arbitrary reparameterizations of the time coordinate. So the derivative term minus, okay, in Schwinger-Dyson equations are is relatively small compared to it's small compared to the self energy. It's relatively small. Okay. And without this perturbation, the equations are invariant. Ignoring it, without the perturbation, equations are invariant under arbitrary reparameterizations of the time coordinate. Right. Okay. So let's go into this in a detail. So the Green's function and the self energy, they need to transform in a definite way under the reparameterizations. Okay, this invariance holds when they transform in a definite way, and the transformation is as follows. So the G should transform, is mapped to G, the Green's function at some new times, right? So f of tau is the reparameterization. But we also need to multiply with the derivative at those two times raised to the power delta. 네. 네. 그러니까 중요한 거는 저 glassy phase가 suppress 됐다는 게 중요해요. 중요한 거는 저 glassy phase가 suppress가 안 됐으면은 슈링거-다이슨 이퀘이션을 풀어서 솔루션이 나와도 그 솔루션이 실제 시스템을 describe 하지 않는다는 거예요. 이 솔루션은 mean field 솔루션이기 때문에 glassy phase에서는 통하지 않거든요. 근데 이제 포인트는 다른 모델에서 이 SYK 모델이 아주 특수한 모델이고 다른 all-to-all 인터랙션이 있는 많은 경우에는 이 transition temperature가 올라온다는 거죠. suppress 되지 않아가지고 이 슈링거-다이슨이 있고 형식적으로는 있고 풀 수는 있어도 이 슈링거-다이슨 이퀘이션의 해가 이 실제 physical system을 describe 하지 않는다는 거죠. 자, 이 reparameterization symmetry랑은 직접적인 관계는 없어요. Okay. So G transforms with f prime to the raised to the delta power. Sigma transforms with derivatives raised to the power 1 minus delta. Okay. Sigma. Okay, so under these transformations, you should be able to check that the Schwinger-Dyson equations are invariant. Okay. And also, you can also check that the zero temperature solution and the finite temperature solution are related by a certain reparameterization f of tau. Okay, so if for example, e.g., okay, zero temperature Green's function. Temperature Green's function can be, which I wrote down before, right? Tau, j tau to the -2 delta can be transformed to the finite temperature Green's function involving the sine function, can be transformed to finite temp Green's function. Green's function using f of tau is proportional to e to the 2 pi I tau beta. Okay. Right, so if you look at this map, it takes the real line to the circle. So this is the mapping that will map the zero temperature solution to the finite temperature solution. And so the point here is that we have a degenerate manifold of approximate solutions. So they're approximate because they're solutions only in the limit that we ignore the kinetic term. But we have a whole degenerate manifold's worth of approximate solutions. Okay, so the manifold of consists of functions of the form okay, right? So any 2-point function that is obtained that is related to the zero temperature Green's function by some diffeomorphism, reparametrization is given here, is going to be a solution. So G, we start with the zero temperature solution. F okay. So we can push the reparametrization to an exponent. Okay, so for an arbitrary, now we've pushed the reparametrization to the circle, right? So for an arbitrary reparametrization of this form, this transformed Green's function is going to be a solution to the Schwinger-Dyson equations. Any questions at this point? So sorry, I've got to be where phi tau takes values on S1 with circumference 2 pi. 2 pi. Okay. So phi of tau you should think of as a mapping, as a map of the circle to itself. Okay, so the original circle has circumference beta. The target circle has circumference 2 pi. Okay. So can we describe what's the mathematical manifold that we have? The set of solutions to our equations are given by all mappings phi of tau, right? So that's the set of all diffeomorphisms of S1. So this is the manifold that we've described here. But there is an exact symmetry that we have to quotient out by, because this this transformation of the Green's function the Green's function is going to stay invariant under certain reparameterizations phi. Okay. So can anyone guess what the symmetry is? What are transformations phi of tau for which the Green's function maps back to itself? So these are the conformal transformations, or SL2R, or to be more exact, it's going to be, the group is PGL2R, projective general linear group, but it's basically an SL2R in terms of the Lie algebra. Okay. So this equation, let's call this equation star. This equation is invariant under certain transformations V of phi tau. Okay. So the equation star is invariant. It's invariant under certain transformations V of phi tau, such that phi, right? So, and V applied to phi define the same G. Define the same G, right? So the idea is that phi and some transformation V applied to phi will always define the same Green's function. Okay, so the symmetry, okay, so these, the V for which these are true, the V, a conformal mapping, so these mappings, these are conformal mappings forming the Lie group PGL2R. Okay. So these are basically the fractional maps. Map Z going to AZ plus B over CZ plus D, right? And where Z in our setup is going to be e to the I phi over tau. So you should check this for yourself as an exercise, that if we apply a transformation to phi of this form, Z goes to AZ plus B over CZ plus D, then this transformation takes the Green's function to itself. Okay, so can we try to understand this a little bit more? So we have a Z coordinate on the circle. After this conformal transformation, what happens? This linear fractional map takes the circles to itself, right? So this defines a mapping, this defines a specific mapping from a circle to the circle. Any questions? Okay. Okay, so these preserving the unit circle. So taking the symmetry into account, what's the exact description of our manifold of solutions? It's diff S1 divided out by the symmetry group. So the manifold of solutions is okay. In the conformal limit where we ignore the kinetic term, it's diff S1 quotient this PGL2R group. Okay, so this is the exact manifold of solutions we have. Now, this symmetry is pretty important here because it exactly corresponds to the symmetries that are present in a two-dimensional hyperbolic disk. This is the connection to gravity. At the level of symmetry, we can see the symmetry matches with the symmetries of a two-dimensional hyperbolic disk. So the idea is that the SYK model lives on the boundary of a gravitational theory on a hyperbolic disk, which is the Euclidean continuation of ADS2. Okay. So how do I draw ADS2? In Lorentzian signature, ADS2 has two boundaries. So ADS2 here. And well, there are many different coordinates that you can use. So, for example, a simple set of coordinates are global coordinates. So you can write d phi squared plus d theta squared over sine squared theta. So those would be coordinates that cover this and two-dimensional anti-de Sitter space like this, where the ADS2 boundaries are at theta equals pi over 2 and minus pi over 2. So these are global coordinates covering ADS2. Now we've been working in Euclidean time, right? The entire time in the SYK model. So we should actually think about the analytic continuation of this Lorentzian ADS2 to the two-dimensional hyperbolic disk. So this analytic continuation sort of works like this. So we can think about coordinates that cover this Schwarzschild patch. And so using Schwarzschild coordinates, the geometry, so these are global coordinates. Okay, using Schwarzschild coordinates, okay, we can write dr squared minus r squared dt squared sorry. 1 minus r squared to the square. So let me just take out a factor of 4 here. So these are coordinates that cover this patch. So the radial coordinate goes out like this. And so if I draw okay, so this would be a line of constant r. And time, this Schwarzschild time, allows you to traverse this line of constant r. So maybe drawing these lines would help, okay? So these are lines of constant t, and these are lines of constant r. Okay. We can analytically continue the Schwarzschild time here, and then we go to the two-dimensional hyperbolic disk. So we get ds squared. Okay. Analytically continue the Schwarzschild time here, and we go to dr squared plus r squared d tau squared over 1 minus r squared. Okay, where now the analytically continued Euclidean time goes around the circle like this. Goes around the disk, sorry. Okay. And on this geometry, the group of isometries is exactly given by PSL2R. So the symmetry matches with the group of solutions at low temperatures. Okay. So the idea is that the conformal symmetry, this group here, PGL2R, or for most purposes, PSL2R, can be matched with the isometries of the two-dimensional hyperbolic disk. And this is a signifier that we are going to, okay, signifier of the duality that we are going to have. Okay, so the conformal symmetry can be identified with that of the two-dimensional hyperbolic disk, H2. Okay. And the degree of freedom phi of tau had in the SYK model, the reparameterization, that's going to be identified with the angular coordinate. Sorry, I want to use phi here instead of tau. That phi of tau is going to be identified with the angular coordinate of some curve that lives on the hyperbolic disk. So think about some curve that lives on the hyperbolic disk. We can define a proper length along this curve, right? That proper length corresponds to our physical time tau in the SYK model. And the angular coordinate, so this point is given by r tau phi tau, right? The angular coordinate phi of tau on the hyperbolic disk is exactly going to be identified with the reparameterization phi of tau in the SYK model. Okay. And phi of tau with the angular coordinate. Phi of tau of a boundary curve on H2. Any questions? So basically, the idea is that the low energy degrees of freedom correspond to those of a boundary curve fluctuating on H2, right? If you had a curve fluctuating on H2, you would naturally expect to have the symmetry, right? That corresponds to the isometry of H2, and that's the situation that we have. Okay, so the low energy degrees of freedom in the SYK model correspond to those of a fluctuating curve on the two-dimensional hyperbolic disk. Okay. And it turns out that when we take the derivative term into account, remember so far in our discussion, we ignored the derivative term. When we take that derivative term into account, the degeneracy of solutions is lifted, right? We said that, so the phi of tau, we said that phi of tau gives solutions, exact solutions when we ignore the kinetic term. But when you take the kinetic term into account, the degeneracy is lifted, meaning that there's an action, there's a cost to each phi of tau. Okay, so it turns out that when d tau is taken into account, we'll count the degeneracy of solutions is lifted. Good. And so for each phi of tau, we have an action, effective action, describing the cost to having that reparameterization, and this is given by the Schwartzian action. Schwartzian of e to the phi tau tau. Okay, where the Schwartzian functional is defined as follows. The Schwartzian of some function f of x with respect to x is given by third derivative over first derivative minus 3 over 2 f double prime over f squared. Okay. So this is the effective action for the SYK model at low energies to leading water in beta J. Now this Schwartzian functional has a PSL2R symmetry. Okay, so it has the right symmetry, and here alpha s is some constant that needs to be determined numerically in the model, right? We don't. Any questions at this point? So this is the leading effective action of the SYK model at. So this is the leading effective action. Leading effective action of the SYK model. Beta J greater than, much greater than 1. 네.
우리가 이 펑션을 파라메트라이제이션들을 이머전스 디그리스 오브 프리덤으로 생각을 하는 상황인 거잖아요.
네.
같은 그린 펑션을 주면 이제 이런 방식만 표현을 표현하고 사실 그린 펑션을 바꾼다는 게 어떤 방식으로 그거를 약간 원래 시오리 관점에서 어떤 방식으로 제도가 되는지.
네. 아.
약간 그거를 뭔가 익사이티드 백그라운드에서
excited background에서 그러니까 그린스 펑션이 바뀌는 거죠. 자, 여기 이 그림에서 생각하면 혹시 더 쉽지 모르겠어요. 그러니까 이런 커브가 있고 커브가 fluctuate 해가지고 커브의 모양이 바뀌는 거죠. 커브의 모양이 바뀌면은 거기에 따라서 그린스 펑션도 바뀌는 거거든요. 그러니까 실제로 이 SYK 모델에서 그린스 펑션 자체가 바뀌는 거예요. 네.
원래 우리가 그 햄사이트에 날라갔다는
네네네.
그 모델 관점에서
네.
이게 뭔가 말하는 플럭추에이션하고 관련을 지을 수 있는.
그러니까 그거는 마이크로스코픽 픽처죠. 네. 마이크로스코픽 픽처에서 이 effective excitation을 describe 하기가 어려워요. 그렇죠? UV에서 IR로 간 거예요. flow 해가지고 IR에서는 완전히 effective description이 새로 생긴 거거든요.
뭔가 이 펑션 자체를 그냥 바이버카라 UF로 생각을 해요.
그쵸, 맞아요. 그러니까 우리가 그 지난 시간에 effective action describe 했을 때 G랑 sigma variable로 넘어갔잖아요. 그 관점에서 생각해 보면은 G 자체가 이제 degree variable이 된 거죠.
일종의 약간
네.
이 펑션에서 뭔가 이 펑션의 라이트 익스테이션을 생각한다.
네, 그냥 fluctuations of the Green's function. 네. G라는 그때 G가 path integral의 variable이었잖아요. 그러니까. 네네. 많이 나와요? 네네. CFT에서 많이 나오겠죠. 왜냐면 SL2R 시메트리가 있어요, 저. 슈워츠이언 펑셔널이 저 F에 대해서 에세트와 트랜스포메이션을 하면은 invariant해요. 그래서 나오는 거예요.
SQL을 보존하는 그런 특별한 컨피그레이션을 찾았고 그냥 이렇게
그러니까 결과적으로 보면은 슈워츠이언 펑션 네, 맞아요. 근데 이게 그냥 시메트리만 보고 맞춘 건 아니잖아요. 이게 사실 이거 드라이브하는 과정을 보여주진 않았는데 지금 현재 이거를 유도할 수 있는 여러 가지 뭐 방법들을 사람들이 찾았어요. 여러 가지 방법으로 이제 유도를 했어요. 이 effective action. 이 effective action이 그냥 하늘에서 떨어진 게 아니잖아요. 다 유도하는 과정이 있습니다. 그러니까 제 페이퍼를 보셔도 되고. 그러니까 일단 어떻게 유도를 하냐면은 effective action으로 돌아가야 돼요. effective action으로 돌아가가지고 유도를 할 수가 있거든요, 이거를. 그러니까 시메트리만으로 맞춘 건 아니고 유도하는 과정이 있다. 그 다음에 아까 또 질문 있었는데. 네? 네, 유도하는 과정. 저 2017년도 제 페이퍼 보시면은 나와요, 슈워츠이언. 근데 그 유도하는 과정을 보면은 하여튼 RG analysis를 합니다. 그러니까 왜냐면 이게 어디서 나왔냐 하면은 제가 아까 말씀드렸듯이 그 키네틱 텀을 틀어서 이게 나오는 거잖아요. 그러니까 그 키네틱 텀을 UV에서 틀어가지고 그게 IR로 어떻게 내려오는지 그 RG 과정을 좀 이렇게 풀면 이게 나오거든요. 근데 이거 유도할 수 있는 방법은 사실 여러 가지가 있어요. 자, 근데 이게 또 어디서 나오는지 제가 그냥 약간 hand wavy하게 보면은 이게 그 Green's function expansion 하면은 이게 또 나와요, 슈워츠이언이. 어떻게 나오는지 보여드릴게요. 이렇게 했어요. So the Schwartzian derivative, where does it? So the action itself, you can do an RG analysis starting from the UV perturbation, but also it just appears in an expansion of the Green's function at short distances. So the Schwartzian derivative comes from following expansion of G. Okay, in powers of the time difference at short distances. So Taylor expanding F and F prime at, okay. So the idea is that we expand an arbitrary Green's function about the zero temperature Green's function, okay. So this so far is just the definition of the transformed Green's function, right? We have a zero temperature Green's function and we transformed it using f of tau. But then if you put this into the formula for the zero temperature Green's function, at short distances we have the following expansion. We have the zero temperature Green's function before the transformation. And then you see the Schwartzian derivative here. Schwartzian of f tau plus times tau 1 minus tau 2 squared. So this is a short distance expansion where you can first see the Schwartzian. And I encourage you to do this as an exercise. Do the expansion at short distances of this reparameterized Green's function and you see the Schwartzian functional appearing. So finally, I want to mention, okay, maybe I'll So when we map the SYK model to gravity, we have certain relations between the parameters, right? So what are the two parameters so far that in the SYK model? Two free parameters. Anyone? SYK 모델에서 파라미터 몇 개 있어요, 지금? 조절할 수 있는 파라미터. n이 있잖아요. n, large n이 있고요. 그 다음에 또 하나 뭐가 있어요? beta j. So those are the two parameters in the SYK model, and they map to parameters in JT gravity, right? So the story is going to be that this Schwartzian action can also be derived as the boundary term in a gravitational theory called Josephine gravity, or JT gravity for short. And the parameters n and beta j, the parameters n beta j in the SYK model are going to map to parameters in JT gravity. Oh, sorry. Yeah, sorry. I'll explain this mapping of parameters later when I describe JT gravity. Okay. Okay, so the next part is going to be about the 4-point function in the SYK model. So far we've looked at the 2-point function. Well, we first looked at the effective action, and then we looked at the 2-point function in some detail, and now we want to go on to the 4-point function in the SYK model. Okay, so okay, so similarly to the 2-point function, we are going to be interested in the leading in large n part of the 4-point function. Okay, so we will compute connected 4-point function. 4-point function at leading order in n. And at strong coupling. Beta j. Okay. So what's the scaling? What's the scaling going to be of the connected 4-point function? Anyone have a guess? 저 학생분 뭐라고 guess 있으세요? 손가락으로 뭘 쓰고 있어가지고 잘 모르겠어요. Disconnected 4-point function의 스케일링이 뭘까요? 혹시 아는 분? 카이스트에서 제 수업 들었던 학생들 중에 혹시 자, 2-point function 스케일링이 뭐였어요? 네, n0. Disconnected 4-point function은 어떤 식으로 날까요? 파이먼 다이어그램이. 그냥 두 개 따로 있는 거잖아. 그러면 스케일링이 뭐예요? n0예요. So the disconnected 4-point function has a scaling that goes like n to the 0. The connected 4-point function is going to be suppressed by 1 over n. So it goes like 1 over n. So the connected 4-point function is going to have diagrams that, okay, so the connected 4-point function, basically these are called ladder diagrams, and they all scale like 1 over n. Dot, dot, dot. Okay, up to some subtleties here, where it depends on whether you average over all sites or not. So let's just write down the 4-point function. So a 4-point function in Euclidean signature is going to look like this: chi I tau 1, chi I tau 2, chi j tau 3, chi j tau 4. Okay. And we can either look at this 4-point function for fixed I and j, or we can take an average over I and j and put a factor of 1 over n squared. So depending on whether you average over the sites or not, the Feynman diagrams differ a little bit in the beginning, but the ladder diagrams always are important. Okay. So what can we learn? What can we learn? What do we hope to learn from the 4-point function? When we compute this 4-point function exactly, in the connected 4-point function exactly, there are roughly two different kinds of pieces of information that we extract. Okay, so information we can extract. Information we can extract from 4-point function. Okay. We go to the OPE limit. The OPE limit is when tau 1 and tau 2 become close, and tau 3 and tau 4 become close. And in that OPE limit, we are going to see the dimension of the bilinear fermion operators, right? So the idea of an OPE in a conformal field theory is that you take two operators close to each other, right? And you can expand the product in a set of third, right? So you have some coefficients Ci, Jk, and you expect to see some new operators O, right? So we can extract the conformal dimensions of these fermion bilinear operators. So fermion bilinear dimensions of fermion bilinear operators. Fermion bilinear operators. Okay, so dimensions of fermion bilinear operators appearing in OPE of 2 Majoranas, of 2 chi's. Okay, dimensions of bilinear operators appearing in OP of 2 fermions. And sort of complementary to this information, which we can extract in a sort of complementary region of the cross ratio. So this is the OPE region when you take these two together and these two together. But there's an OTO region of the 4-point function where you take tau 1 and tau 3 to be together, and tau 2 and tau 4 to be together, and the two pairs to be far apart. So that's the OTO out of time order region. And in that region, in the OTO region, we see when we analytically continue back to real time, so we do the computation in Euclidean signature, and we continue to real times, we are going to see what's called a Lyapunov exponent. Okay, so this is an exponent where the 4-point function has a piece that grows like e to the lambda t, where lambda is going to be 2 pi over beta. Okay, so this is the exponential growth in the OTO 4-point function. Exponential growth in the OTO 4-point function. OTO 4-point function. And this is directly connected to black hole physics, to the physics of an excitation going into the 2-dimensional black hole. as this excitation falls into the black hole, well, just think about a classical particle. Just by considering a classical particle falling into the black hole, you can show that its energy, its local energy, so the energy measured in a certain frame, okay, which is boosted in the right way so as to represent the point of view of an observer. So if you measure the excitation of this particle at Schwarzschild time t, from the point of view of an observer at the boundary at Schwarzschild time t, you will see that local energy grows like e to the, I'm going to call it kappa here, e to the kappa t, where kappa is 2 pi over beta of the black hole. And this is a new piece of physics that was discovered in the SYK model, that exponential growth of energies, of local energies, is visible in the SYK model as the exponential growth of the out-of-time order 4-point function. So next time we are actually going to compute the 4-point function and try to continue with extracting this information. 자, 오늘 여기서 마치고 질문 더 받을게요. 질문 있으면. Any questions? 네. 저 phi가 degree of freedom이잖아요, 지금. 왜냐면 각각의 phi마다 다 다른 그린스 펑션이 있었으니까. 그러니까 phi가 뭐예요? set of all phi's 생각해보면 diff S1이죠. 그 다음에 왜 quotient 해줘야 돼요? quotient 해줘야 되겠죠. symmetry, exact symmetry가 있었으니까. symmetry가 아까 그 그린스 펑션 각각의 phi에 대해서 그린스 펑션을 define 하잖아요. 근데 어떤 주어진 phi가 있어요. 근데 그 phi에 대해서 그 V라는 맵을 compose 해요. 아까 SL2R. 그 맵을 compose 하면은 똑같은 그린스 펑션이 invariant 하다는 거예요. 아까 그 각각의 파이에 대해서 그린스 펑션을 define 한 게 어디 있었는데? 지원. 네네. 픽스하지 않아도 될 것 같은데? 픽스해서 해도 될 것 같아요. 네. 네. 네? 파이, 네. 네네. B가 아까 그 AZ plus Z goes to AZ plus B over CZ plus D. 자, 제가 자, 이 zero temperature 그린스 펑션이 아까 있었잖아요, 분명히. 거기서 시메트리가 결국엔 나오는 거겠죠. 자, 이렇게 쓰고 나서 그 다음에 F tau1 델타 F tau 이렇게 됐었잖아요. 아까 이 G 베타 인피니티 tau 이건 아까 뭐였어요? 마이너스 B 델타 J tau1 마이너스 tau 이렇게 됐었잖아요. 그렇죠? 그러니까 그리고 지금 여기서 f of tau는 e to the I phi tau예요. 자, 그러면 각각의 phi마다 각각의 파이마다 지금 새로운 그린스 펑션이 정의되는 거죠. 이 식으로 인해서. 근데 파이랑 v compose 파이랑 이 식에다가 집어넣으면은 똑같은 그린스 펑션이 생긴다는 거예요. 왼쪽. 그게 시메트리인 거예요. 근데 아까 v가 뭐였어요? v의 형태가? v의 형태는 아까 이런 형태였잖아요. v는 z가 az plus b over cz plus d. 이런 형태였잖아요. 이제 얘가 가요? 네. So the question was, why is this a symmetry? Like, in what sense is V a symmetry? So it's explicitly defined by this equation, right? Because this equation gives you a G for each reparameterization phi. And the idea is that if you insert in this equation phi and V acting on phi, you get the same left-hand side. So that's the sense in which V is a symmetry. 더 질문 있어요? 네, 그러면 다음번에 4포인트 펑션 할게요.